Let's prepare on the theory of simple bending. So now we are going to see about the theory of behind the simple bending process. Okay, so here first let us see what is pure bending. So pure bending means when a beam or something is experiencing only the bending moment and there is no shear force created there. Okay, so at that point only the pure bending will be happening. Okay, and then neutral axis. So neutral axis is nothing but it passes through the center of gravity and the strain changes its sign. Okay, so if you are taking a rectangular beam like this means the strain will be like this. So this point is only called as the neutral axis. So here this is the pure bending equation. M by I is equal to F by Y is equal to E by R. Okay, so here M is the bending moment, I is the moment of inertia, F is the stress here, and Y is the if you are taking a fiber, the distance of that fiber from the neutral axis. So that is only taken as Y here, and E is the Young's modulus and R is the radius of curvature. So based on these formulas only, the whole this chapter is based on this only. So there is a easy trick to remember this, that is nothing but may I follow you Elizabeth Rani can be a trick to remember this formula. So it will be easy for you. Okay, and then the curvature is nothing but it is 1 by R. Again it is equated from this formula only, is equal to M by EI, and M is equated as Fi by Y. Okay, so here this I is taken here, so it is Fi by Y. So I by Y is nothing but it is the section modulus. So section modulus also we have seen already in the previous unit. So here M will be equal to F into Z. So it means that M is directly proportional to Z. So what they are telling here means the strength, because bending moment is nothing but it mainly means the strength of that particular body, no? So here the strength depends on the section modulus. So this is an important outcome of this formula. And then comes some important assumptions and important notes to be taken here. That is, every layer in that beam or any body is free to expand or contract, and the Young's modulus has same value for both in tension and in compression. And then the strain is directly proportional to the distance from neutral axis. So this also they have taken from the formula only. E by R is equal to F by Y, no? So E can be expanded as stress by strain. So that is only sigma by E is written here, and here it is clearly showing that the strain is directly proportional to Y. So that is only they are telling here the strain is proportional to the distance from the neutral axis. And then the summation of the compressive force above the neutral axis will be equal to the summation of the tensile force below the neutral axis. And then if you are taking a solid circular section means it will be less economical when compared to the rectangular I section and hollow section, because the reason is the Z of the circle is very less. So Z means section modulus is very less, so the strength also will be very less, so they mean that it is less economical also. And then F is equal to M is equal to Fi by Y. Again they have written like this. So here F by Y and I by Y is nothing but Z, so they have denoted as F into Z. So F is only again written as stress here, and this will be equal to B d square by 6, because this Z section modulus for a rectangular section we have already studied, it is B d square by 6. So from this what they are coming to convey is M is proportional to D square and M is proportional to D. So this both points are very important, because they will be asking like this, based on the depth how the moment is differing. So the options will be square of the depth or cube of the depth, like that they'll be asking. So these 2 points are very important. And then comes the composite beam. So composite beams means it is nothing but a combination of two different metals. Okay, so here if you are taking a body like this, okay, so this will be of timber material, and the left and right side material, no, so it will be of any other steel metal like that. Okay, so if two different materials are combined like this to give a composite beam means the width should be taken as the equivalent width here. So here the equivalent width will be equal to B plus 2MT. Okay, so what does this B and M and T means the B is the width of the center material. If you are assuming it as timber means the width of that timber material, plus 2 into m. M is nothing but the modular ratio. So it will be equal to the Young's modulus of the steel divided by the Young's modulus of the timber. So I am telling an example only, that is the lesser material only will be at the two sides and larger material will be in the middle. Okay, so the Young's modulus of that lesser material only should be divided by the this metal, that is A metal. Okay, so here always it should be like that, the Young's modulus of B should be greater than the Young's modulus of A. So it should be always like that, so that the value of M will be always greater. And then the flitched beam, so again they are telling this only here in terms of Z they are mentioning it. That's all we know. For that is the Z for rectangular section, it is B d square by 6. No, so instead of B I have written this B plus 2 empty here, that's all. And then for the beams over one another, so it means if two beams are attached to one another and if they are rigidly connected means it will be acting as a single beam, but if they are not connected and simply they are placed means it will act as a separate beams only. So that is only I have drawn a diagram like this. The strain diagram, if they are not rigidly connected means it will be acting separately only. If it is rigidly connected it will be like this. So here they are equating M is equal to EI, so that when you are taking a ratio of that, M1 by M2 will be equal to E1 I1 by E2 E2. So this formula will be helpful in solving the problems regarding this beams placed one another. And then here some important points are to be noted. So these are the outcomes of this strength, bending moment and everything based on this pure bending concept. So these points are very important. First let us see the rhombus and square. Okay, so if you are taking a rhombus member and a square member means when you are taking the strength, so here I have written as S, no, so it means the strength, so which is equal to the Z is section modulus. Already we have seen that the moment bending moment is proportional to Z, so it means that the strength is proportional to Z. So I am equating strength of the rhombus is equal to Z of rhombus equal to. We have already studied the section modulus for square and rhombus in the previous unit. For square or rectangle anything, it's B d square by 6, and for rhombus it is B d square by 6 root 2. Okay, so when you are taking the ratio, obviously it will be 1 by root 2 only. I am written this in the value also, it is 1 by 1.414. So it means that the square is root 2 times stronger than the rhombus, so it is 1.414. This 1.414 means that it is 41.4% and extra is given there, extra strength is provided. So this means that the square is 41.4% stronger than the rhombus. So these values ought to be noted. And then comes the rectangular section. So here what they are telling us, when you are cutting a rectangular section from a circular body, the maximum strength could be obtained when you are maintaining this ratio. So when you maintain this ratio and cut means only you will be getting the maximum strength. So the ratio is given as h by b. H is nothing but the depth is given, so h by b is root 2. So here also they have given the breadth and the depth also separately. So the breadth should be equal to d by root 3 and the h should be equal to root 2 by root 3 into d. Okay, so if this is obtained means obviously h by d will be, the ratio will be root 2 only. So this will give you the maximum strength. Then the third note is what means, here they have taken a square section and they are cutting the top and bottom corners, they are flattening it. Okay, so that the strength is actually increasing. So how they are flattening it means they are flattening nearly 1 by 9 of y. So that much depth is flattened in the top and bottom, so that the increase in the section modulus will be 5.35%. So as there is the increase in the section modulus, the bending stress will be reduced by again the same value. So this is also one point. And the fourth important point is they are taking again a circular section and flattening it. So when you will get the maximum strength means when you are flattening it to a depth of 0.011 d. So d is the diameter of that circular section, and here the strength in that is the increase in strength will be 0.7%. So these are the important values to be studied based on the section modulus and the strength of those beams. And the last is the ratio of the weight is given. That is, if you are taking 3 beams having the same length and same bending stress and they are subjected to the same bending moment. So everything is same, only the shapes are different means the weight ratio. So if you are taking the weight ratio means it will be very lesser for the rectangular section than the square section than the circular section. So the value is given as 0.8 is to 1 is to 1.2. Okay, so these are the ratios of the weights. So it is again equal to the strength only. So again they are talking the mean of strength. So here this rectangular section will be having a greater strength, and the most economical section is also rectangle only. Thank you, and keep watching for the next lecture on shear stress.